Hello everyone. Today we are going to analyze this beam using a slope deflection method. Before analyzing, let's see the slope deflection equations. For every span, there will be two slope deflection equations. Consider a random span AB in a continuous beam. For this span, we are having two slope deflection equations. In these equations, MFAB is the fixed end moment at A, MFBA is the fixed end moment at B, theta A and theta B are the slopes at A and B respectively. 6EI delta upon L square is the fixed end moment due to sinking of the support. If in the question nothing is mentioned about the sinking or settlement of the supports, we don't have to consider this term. In the given beam also, there is nothing mentioned about the sinking or settlement of the supports. So we can assume that there is no settlement in the given beam. So we don't have to consider these two terms. We had a brief introduction about slope deflection equations. Now let us see the beam. In this beam, there are three spans: span AB, span BC, and span CD. In the span AB, there is a point load 20 kN acting on the center. In the span BC, there is a point load 25 kN acting at 2 meter from the support B. In the span CD, we are having UDL 12 kN per meter acting for the full span. In the point A and in the point D, there are fixed supports. In the point B and in the point C, there are hinged supports. The moment of inertia for the span AB is 2I. For the span BC, it is 1.5I. For the span CD, it is 0.8I. Span AB is 4 meter long, span BC is 5 meter long, and the span CD is 4 meter long. In this beam, we have to calculate 6 moments. In the fixed support, there will be a moment. So, in the point A and in the point D, we are having moments. In the point A, we are having the moment MAB, and in the point D, we are having the moment MDC. In the joints, there will be two moments. In the joint B, we are having two moments MBA and MBC. Also, in the joint C, we are having two moments MCB and MCD. So, totally we have to find 6 moments. Also, we have to calculate 4 vertical reactions RA, RB, RC and RD. Now, let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now, let's see the formulas to calculate the fixed end moments. In this table, you can see some of the important fixed end moment formulas for the different type of loadings. In the span AB, there is a point load acting on the center. So we have to select this condition. The formulas are minus WL upon 8 and positive WL upon 8. In the span BC, there is a point load. That point load is not acting on the center. So we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. In the span CD, we are having UDL acting for the full span. So we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let us apply those formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is acting in the center. We have already seen the fixed end moment formulas minus WL upon 8 and positive WL upon 8. M of AB will be negative because it is acting in the anticlockwise direction. M of AB will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 20, L is 4. After calculations, we are getting M of AB is equal to minus 10 kilonewton meter and M of BA is equal to 10 kilonewton meter. Now let us calculate the fixed end moments in the span BC. In the span BC, there is a point load. This point load is not acting on the center. We already saw the formulas for the fixed end moments minus WAB square upon L square and positive WA square B upon L square. Let us apply the values inside the formulas. W is 25, A is 2, B is 3, L is 5. After calculations, we are getting M of BC is equal to minus 18 kilonewton meter and M of CB is equal to 12 kilonewton meter. Now let us make the fixed end moments in the span CD. In the span CD, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments minus WL square upon 12 and positive WL square upon 12. Let's apply the values inside the formulas. W is 12 and L is 4. After the calculations, we are getting M of CD is equal to minus 16 kilonewton meter and M of BC is equal to 16 kilonewton meter. In the slope deflection method, we have to see the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. Also, in the roller support, there will be slope. In this beam, in the points B and C, there are hinged supports. So, the number of supports where slope can occur is equal to 2. In the point B, we are having theta B, and in the point C, we are having theta C. So, in this analysis, there are two unknowns. If we calculate these two unknowns, we can easily find the final moments. To find these two unknowns, we need two equilibrium equations. Now, let's see how to make equilibrium equations. First, we can make equilibrium equations in the joints because in the joints the summation of the moments will be 0. Then we can make equilibrium equations in the ends of the beams. In the fixed end there will be a moment, so we cannot make equilibrium equation. In the hinged end there will be no moment, so we can make equilibrium equation. In the roller supported end also, there will be no movement, so we can make equilibrium equation. In this beam, first let us check at the ends. In the ends A and D, we are having fixed supports. In the fixed supports, there will be movement, so we cannot make the equilibrium equations. Now, we do not have any other option. We have to see only at the joints. In this beam, there are two joints, joint B and joint C. The summation of the moments in these joints will be 0. In the joint B, we are having two moments, MBA and MBC. When we add these two moments, it will be 0. In the joint C also, we are having two moments, MCB and MCD. When we add both of them, it will be 0. In this analysis, we needed two equilibrium equations. and we have formed them. Now let us start making the slope deflection equations. First, in the span AB, let us make the equations. In the equations, let us apply the fixed end moments. For AB, the moment of inertia is 2I, so instead of I, we have to apply 2I in both of the equations. Length of AB is 4 meter. In the point A, we are having a fixed support. In the fixed support, there will be no slope, so theta A will be 0. Finally, in the span AB, we are making two slope deflection equations. Now, let us make the slope deflection equations in the span BC. First, let us apply the fixed end moments. The moment of inertia for BC is 1.5I. So instead of I, we have to apply 1.5I in both of the equations. Length of BC is 5 meter. Let us apply that. Finally, in the span BC, we are making two slope deflection equations. Now, let us make the slope deflection equations in the span CD. First, let us apply the fixed end moments. For CD, the moment of inertia is 0.8I. So instead of I, we have to apply 0.8I. Length of CD is 4 meter. Let us apply that. In the point D, we are having a fixed support. In the fixed support, there will be no slope, so theta D will be 0. Finally, we are making two slope deflection equations in the span CD. Now, let us make the equilibrium equations. We already know we can make the equilibrium equations in the joint B and in the joint C. In the joint B, MBA plus MBC will be 0. For MBA and MBC, we have already made the slope deflection equations. Let us apply them. After adding the values, we are getting the first equilibrium equation. Let us keep this equation as number 7. Now let us make the equilibrium equation in the joint C. In the joint C, MCB plus MCD will be 0. Let us apply the values of MCB and MCD from the slope deflection equations. After adding the values, we are making the second equilibrium equation. Let us keep the equation as number 8. Now we can use the calculator and solve these two equations. If you do not know how to solve two equations in the calculator, see the description below. You can click the link and watch the video. After solving these two equations, we are getting Ea theta b and Ea theta c. After applying the value of Ea theta b in equation number 1, we are getting MAB. After applying the value of Ea theta b in equation number 2, we are getting MBA. After applying the value of Ea theta b and Ea theta c in equation number 3, we are getting MBC. After applying the value of Ea theta b and Ea theta c in equation number 4, we are getting MCB. After applying the value of Ea theta c in equation number 5, we are getting MCD. After applying the value of Ea theta c in equation number 6, we are getting MDC. In this analysis, we have calculated all of the moments. In this analysis, we have calculated all of the moments. For MAB, we are getting a negative value. That means MAB is acting in the anticlockwise direction. In the point B, we are having two moments. For MBA, we are getting positive value because it is acting in the clockwise direction. For MBC, we are getting negative value because it is acting in the anticlockwise direction. In the point C also, we are having two moments. For MCB, we are getting a positive value because it is acting in the clockwise direction. For MCD, we are getting a negative value because it is acting in the anticlockwise direction. Finally, for MDC, we are getting a positive value because it is acting in the clockwise direction. Now let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two movements, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take movement about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction. So it is positive and the distance is 4 meter. So for RA, the point load 20 kN is acting towards the point B in the anticlockwise direction. So it will be negative and the distance is 2 meter. So 20 into 2. Then there are two movements. 7.75 moment is acting in the anticlockwise direction, so it will be negative. 14.5 movement is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 8.31 kN. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RV1. In this span, there are three forces. RA and RB1 are acting upwards, so both are positive. Point load 20 kN is acting downwards, so it is negative. We already know the value of RA, let us apply that. In this way, we can get RB1, which is equal to 11.69 kN. Now, let us calculate the reactions in the span BC. In the span BC, there are two movements. MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The point load 25 kN is acting towards the point C in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 25 into 3. Then we are having two movements. 14.5 is acting in the anticlockwise direction, so it will be negative. 14.94 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2 is equal to 14.91 kN. By applying the rule, summation of vertical forces is equal to 0, we can calculate RC1, which is equal to 10.09 kN. Now, let us calculate the reactions in the span CD. In the span CD, there are two movements, MCD, which is acting in the anticlockwise direction, and MDC, which is acting in the clockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. The vertical reaction RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RC2. The UDL 12 kN per meter is acting in the anticlockwise direction towards the point D, so it will be negative and the distance is 4 meter. When the UDL comes, we have to multiply with the distance and the distance by 2. So 4 into 4 by 2. Then we are having two movements. 14.94 is acting in the anticlockwise direction, so it will be negative. 16.53 is acting in the clockwise direction, so it will be in positive. Finally, we are getting RC2, which is equal to 23.6 kN. Using the rule, summation of vertical forces is equal to 0, we can calculate RD, which is equal to 24.4 kN. Now, let us add RB1 and RB2. After adding, we are getting RB, which is equal to 26.6 kN. Also, let us add RC1 and RC2. After adding, we are getting RC, which is equal to 33.69 kilonewton. Now, we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A and towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the diagram. Now we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Finally, we have to combine both of them to get the bending moment diagram. For the free moment diagram, we have to assume every span as a separated simply supported beam. First, let us take the span AB. In the span AB, a point load 20 kN is acting on the center. If a point load is acting on the center, the bending moment formula in the simply supported beam is WL upon 4. Here W is 20, L is 4. When we apply inside the formula, we are getting 20 kN meter. In the simply supported beam, if the point load is not acting on the center, the formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 2, B is 3, L is 5. When we apply inside the formula, we are getting 30 kN meter. In the simply supported beam, if the UDL is acting for the full span, the formula to calculate maximum bending moment is WL square upon 8. Here W is 12, L is 4. When we apply inside the formula, we are getting 24 kN meter. Using these three values, we can draw the free moment diagram. Now let's see how to draw end moment diagram. For drawing the end moment diagram, we have to see the direction of the curves. First, we have to arrange these movements in the curves. For MAB, we are having a negative value because it is acting in the anti-clockwise direction. So, in the point A, we have to make an anti-clockwise curve towards the point B. For MBA, we have a positive value. That means it is acting in the clockwise direction. So, from the point B towards the point A, we have to make a clockwise curve. For MBC, we are having negative value. That means it is acting in the anti-clockwise direction. So, from the point B towards the point C, we have to make an anti-clockwise curve. In the same way, we have to make the curves in the point C and in the point D. Then, we have to see the direction of the curves. All of the curves are indicating upwards. That means the end moment diagram comes above this line. Finally, we can connect the values and make the end moment diagram. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the points are coming above this line, so it is negative. Now, let us combine the free moment diagram and end moment diagram and make a bending moment diagram. Here you can see that I have combined both of the diagrams. If you are very experienced, there is no need to make the end moment diagram and free moment diagram. We can directly make the bending moment diagram. Wherever the free moment diagram and end moment diagram are alone without mingling with each other, we can mark the values. Here the end moment diagram, here free moment diagram, end moment diagram, free moment diagram, end moment diagram, free moment diagram, finally end moment diagram. Wherever they are together, we are not marking anything, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.